Alrighty, so hello and welcome. I have another problem to look at today. So I wanted to look at the longest palindromic subsequence question again. I'm trying to get a more efficient approach. I was thinking about just looking at the let's get right into it, I think. I was thinking about getting right into we'll get right into it. So I was thinking about trying to optimize this, trying to make, not just optimize this, but come up with a faster solution. And I don't really have one. We could look at the discussion. I'm almost certain there's something in the discussion that's good, that's sort of plausible or decent. But where we were last time, we were saying like there might be, like you could have something like A, B, C, B, A, C, B, A, right? And you could do something where you pair off your outermost characters, and you can create kind of like an onion, where if you had like, for like all the A's, for instance, where you have like, if you had like A, just have some random characters and a few A's in there, something like this, quote unquote the onion, right? Onions have layers, so you have A and A, it's one layer, and then the next A and the next A is another layer, right? And you have something like this. And the idea is something like you want to efficiently determine the sequence of characters, sequence of layers that will give you the longest palindromic subsequence. Obviously, I mean that's the statement of the problem, but I guess in theory you could use these sort of layers to put together a kind of well, what I was looking at before is like a graph where the nodes are, you sort of have the nodes sort of have two data points. So this would be like 0 and n-1, right? N is the size of the string, and every pair that you could find would be sort of like another node in that graph, and every pair would be another node in that graph, and you would have an edge from one node to the next if and only if you call it sort of A and B would be one node's I guess left and right indices for that pair, and then C and D would be the other nodes left and right indices. Then A has to be less than or equal to, or A has to be less than B, and C has to be greater than D, right? So you have to have kind of like a basically the edge represents, that means that these two pairs could be connected or used together. They don't interfere with each other. In other words, they don't have like something like this going on, right? So like this D and D breaks this A and A pair, right? So you don't have that kind of behavior. Now if you have a graph like that, there's some interesting properties where the first things first, it's transitive, this property, right? So obviously if we have an inner pair in here like S and S, if that's inside of this A and A pair, and this A and A pair is inside of this other A and A pair, that means that this S and S pair is also inside of that outer A and A pair. So it's not really, you're not really looking for like those edges. You actually don't really care about the transitive edges. You want the edges that are sort of like the primary edges, I guess you might call them. And what I want to say is, I want to say that you can show that if you only consider these primary edges, that you can find an efficient way to solve this problem. Like if you build this graph and you only consider the primary edges rather than the transitive edges. Because the tricky thing is that you could build this graph, but the problem is if the edges are transitive, you run into an issue where the edge graph could be quadratic. It could be a complete graph. It could be all the edges could exist, and then if you traverse all the edges for whatever reason, then you're stuck with a quadratic time algorithm, which is the one, by the way, the algorithm that I've written so far, I believe, is quadratic. I think so. Which is not efficient enough for what we want. I mean, I think this is something more efficient we can do. But if we somehow prune the transitive edges, then we may be able to show that actually the solution we're looking for really only requires us to go through a linear number of edges. That's what I'm trying to go for. That's what I'm trying to get at. However, it's challenging. It's definitely a challenge here. I don't really know how to do this. So you can break up, as I said before, you can kind of break this up into the different characters. We'll just do A, B, and C, or D, I guess. And you could say there's sort of like there's sort of these like subsections of the graph where we know how these nodes are related to each other. So we have one node for A connects to another node, right? There's these two pairs. And then B has, I don't think B has any other characters in the string. I think it's just one. C, so B doesn't have any nodes. C is, I don't think there's any C's. I don't see a C. Yeah, there's no C's. And then D has, I'll put it in green. Also, my eyes hurt for some reason. D has one here. And another D here. And I guess just for the sake of argument, we'll include S as well. We'll do that in blue. What this algorithm I'm describing might look like. Now this isn't the full graph because I don't want to do the full thing. But D has two, right? So D has these two nodes, right? One contained in the other. And then S has, let's do blue. S, there's the leftmost S and the rightmost S, so these two S's. Actually, all of these do create these kind of layers neatly, which is nice. And there's an S and S here. Yeah, actually that's interesting. It just kind of randomly happened that way. But there's an S and S, and another, the next S also is the most to the right of it's an S that's pretty close. So S has two layers too. And like these are sort of like subgraphs, I guess, of the whole graph. And they don't necessarily need to be like that. Well, actually, I guess by definition, because these characters are, you can orient yourself in such a way where these are all of the connections you can have. There's another problem here too, by the way. Actually, I didn't even really think about this or notice this, but it may actually be more advantageous to not group and organize the pairs of characters in this way, because you could have a situation where the best subsequence, actually you would have something breaking where you might actually want to connect these characters like this. So actually I think I'm wrong about what I was saying before the other day about I think I was wrong and I'm wrong about like it might, yeah, like you might have a situation where it's actually advantageous to use this part for A and A rather than to use the other sort of possibilities. And that kind of blows a big hole in all the things I was saying the other day about like creating a graph and finding the deepest path to the graph. I don't think that actually works. I'm gonna lay down and think about this more. Just gonna lay down and think about it. I'm a little bit tired, but also I think I was wrong from the other day. I think this whole idea about using a DAG and trying to use a topological sort of some kind just doesn't cut it. Just doesn't cut it. How much time we have? 9 minutes in. Yeah, just doesn't work. So interesting. Yeah, but like I said, because you may actually want to select different pairs for your subsequences to create the largest palindrome. So you actually don't necessarily want to limit yourself ahead of time by breaking things up in this way. Well, excuse me. We can still use this approach that I just described somewhat if we use a divide and conquer approach, and we say we need to have the longest palindromic sequence that has a sort of a focal point in the middle, right? Where what I just described ultimately would force us to kind of look at it the way that I was just talking about, where because all the characters that are associated with the palindrome need to be on the other side of a fence, so to speak, it forces us to not be able to break it down and use sort of like I guess palindromic elements on the left side or the right side only. Like you won't be able to do that because they won't be available, I suppose. Yeah, by the it won't be available by the approach that we're taking. That opens us up to an n-log-n divide and conquer solution, and that also allows us to continue to consider what I was just saying. Then in that case, actually, the things I was saying make sense. But if not, if you are allowed to kind of venture off into the left side or the right side, then then it kind of breaks down. But okay, so maybe we'll go for try to go for an n-log-n solution. I think in an n-log-n solution though, you still have a situation where you don't actually need to do divide and conquer. You can do you can use a not a sorting approach, but like I guess you could do some pre-processing. Excuse me. And when you look for elements, you can recursively search for elements. You can do it in logarithmic time instead of linear time. And this is what I was describing before about like you could take the two outermost elements of it for a particular character and then recurse on the subsequence that's contained between those two elements exclusively, right? Not including those two endpoints. I mean, excuse me. I don't know how much more efficient things become if we do that in logarithmic time, though. It's actually finding each of those pairs. Let's see. Well, if we look at our loop, we say it's O of log n time for each character, and then there's a recursive step. Sort of 26 times. So 26 times this logarithmic factor plus the recursive step. Yeah. I want to say we can use there's also another element of like that recursive part, depending on what result we got. Excuse me. Like, I guess the worst case would be if we only eliminated two characters at a time, right? Let's do it that way. Let's do the worst case. Worst case analysis. Only eliminate two characters at a time. So this function that we're calling would need to operate on a excuse me. Oh, sorry. Sorry, I'm really tired. In the worst case, this would need to operate on a I guess it's O of n minus 2 sized sequence. Yeah, I mean, actually, what's interesting about that is that the logarithmic search is kind of meaningless because it's only costs you one step actually to go to that spot. So I don't know. I think in that case you really aren't. I think you're linear in that case because you would do constant work at each iteration, and then you're doing n-2 all the way down to 0 to 1 or 2, or yeah, one, yeah, I guess 0, 1 or 0, however you want to look at it. And so that's roughly roughly O of n times O of 1, which is just O of n. So it's linear work in the worst case, sort of. That's not really the worst case, but in that case, the thing I think that happens though is that you end up doing kind of of unbalanced work because you're looking for different characters each time. So I think in some cases you do a linear amount of work rather than a constant amount of work, and I think that's what makes it quadratic. However, if you do logarithmic work every time, in the worst case, which you can guarantee that, then I think you're looking at O of n log n time, which is fine. Actually, that's probably what I should be shooting for. So actually, I think I just need to not sort, but use use just a pre-processing step and some. It is that simple. I wonder if first off, I wonder if you can do this in a way that's actually linear time and not n log n time. And then secondly, I wonder what's the wonder ball? Excuse me. Yeah, I think I actually think that's the reason. I think that's the problem is that you do potentially linear time at every step just to find that pair. And in some cases you won't do a linear amount, but in some cases you will because you'll like every step you search again for all the different characters from that position. I think actually I think the way that I wrote this is really bad because we already know. Well, no, never mind. No, that's fine. No, I take that back. Well, actually, I'm kind of pondering it now. I wonder if I can rewrite this such that when you look for the pair, when you look from left to right, you don't actually search for the leftmost character. In other words, instead of finding the leftmost and rightmost characters, you just basically assume the leftmost character, and and you basically assume that the character you're looking for is the one you're on top of already. And the reason you would do that is because you've already found a character there. It's already something there to search for. And the other characters, as you kind of, I guess, reach them, they are eventually going to be. See, the problem with that though is I'm not sure if the algorithm is correct if you do that. That's why I'm hesitant to do that. But I think that actually would make things linear time as well. Would make things a lot more efficient. Instead of searching over all of the characters and all of the outer pairs that exist, you only search for. You really just search for the outer pair for the given character at present. And I guess the reason is that if there is a subsequence that's optimal, then I suppose it would be contained by that outer subsequence, or that outer pair, that pair. I mean, I suppose, I don't really know. Well, I guess, no, yeah, I don't think that's correct, because you could end up cutting off a huge chunk of the right side by including that particular character. Yeah, at that point, like you don't necessarily, like your optimal solution doesn't necessarily contain that character. That's the issue. That's why it wouldn't necessarily be correct. Probably be a lot more efficient, but it won't necessarily be correct, because you may not actually use that. Excuse me. Now, what's interesting is you can compute that, in other words, that path, that if you were to include that that character and then find its outermost, so the rightmost matching character, if you were to include that, or not include that, right? You can do both of those calculations and take the maximum of those two. I think the problem with that though is I guess there's sort of a lot of different options you could pick for S, or not for S, for that particular character you're looking at. Yeah, you could have like a whole sequence of these characters show up in your string, and yeah, I don't know about that. May not necessarily be the rightmost that you want to use, although that is kind of optimal actually. So I take that back. It kind of always is the rightmost that you'd want to use. No. I take that. No, that's not true. No, because yeah, no, it is true. That's actually true. Anything that would fit between those two characters would also anything that would fit between the sort of more inner possibilities would also fit in the more outer possibilities. So actually, it's optimal just to always take the rightmost. But yeah, really the question is whether or not you want to take that pair at all, because you may be eliminating other pairs that you'd want to use. That would be more advantageous. Right. Yeah, I think there is kind of a recursive, I guess, maximum selection you can do where you say you can choose between selecting or not selecting that particular value, and you take the maximum result of those two possibilities, and obviously those two possibilities are done recursively, so you get the maximum of those two possibilities at that point, or the maximum possible of those two possibilities. I think it can work. Huh. I really do think the optimal thing to do is to just, instead of using a linear search in our iteration, to use logarithmic search. I really do think that's actually the problem, and that our algorithm will just be really fast enough if we just change that and call it a day. All right, let's do that, because I can't seem to come up with an obvious linear time algorithm. So we'll just use what we have and make it, try to make it n log n. Wow, I am really sleepy. Thinking maybe I should take a nap. I think that's not a bad idea. We can maybe code up this approach, this solution with this pre-processing step, and then from there we can try it out, see how efficient it is, and then take a nap. Then take a nap. 1,000 log base 2, I think, is 10, right? 2 to the 10th is roughly 1,000, yeah. So we're going to go from a factor of about 1,000 to a factor of about 10. So our algorithm is going to be about 100 times faster. Yeah, that sounds about right. That sounds about right. Take 4 milliseconds, 4, 5, 6, 7, 8, 9, 10 milliseconds. Something along those lines, around 10 milliseconds to execute. All right, let's try it. Let's try it. Yeah, what I was saying before about topological sort and whatnot was just incorrect. Oh, it's just incorrect. Okay. So let's try our, excuse me, what do they call that? Pre-computation, pre-optimization, I guess. Pre-computing, yeah. Yeah, pre-computation. So we'll say for each character, excuse me, in the character set, we want to create a vector and this is going to be of ints. It's actually going to be a vector of ints. This should be interesting here. So it's a vector of ints, 26 of these, so we'll call it V, or we'll call, did I use V? Yeah, let's use V. V, 26, and it's going to be standard vector of ints of size s dot size, and they're all going to have zeros, zero index. Actually, they should be iota. Oh, not iota. Yeah. No, not this dot size. No, it's actually. We don't know what the size is. They're actually just empty vectors. Okay. And we're going to say for int I equals 0, I is less than s dot size plus I. So this is going to be O of s times the character set. Ultimately, the algorithm is O of s times n log n, where O of n, yeah, or excuse me, yeah, O of s times the size of the character set is ultimately O of, or make it n, O of n times the character set size. We can do O of n log n times the character set size. So we're going to say if s of I is equal to c, then we're going to take our v of the character, and we'll do c minus a, and we're going to push back this index. So we'll keep track of all of the indices for each character. Right? It's basically what we're doing. We're creating kind of a partition of the indices for each character. And now, when we look for the leftmost and the rightmost, we can actually use an algorithm. I'd be a little more clever about this by saying using the upper bound. So we're looking for a character that's so we're looking from left to right. We're looking for the first index that matches this character that's greater than this left value, right? So we'll say int leftmost is equal to standard upper bound. So strictly greater than is upper bound, right? Greater than or equal to is the lower bound. So yeah, because if we get a whole sequence of things that are equal, then greater than or equal to will be if they're all duplicates, it'll be on the leftmost side, the lower bound, and if it's greater than, it'll be the upper bound. So greater than is the upper bound. We want upper bound of, it's going to be v of c minus a. So we're going to say auto reference, we'll say const auto reference which array. It's going to be v of c minus a. And we're going to say which array dot begin plus left, which array dot end, and we're going to use the value left. I think that's correct. That's leftmost. The rightmost, on the other hand, is going to be similar . However, it's going to be, I guess if you go backwards, maybe, something like that. You're going from right to left. You're looking for the first so if you went the other direction, you went backwards, it would be, what would it look like? It would say, you're looking for, on the right side, you're looking for the first index that's less than, strictly less than the right. Which actually is just right minus 1, I think. It's just, yeah, I think it's just right minus 1. Well, no, it's not right minus 1. It's, right, I think that's part of the problem, is that you don't necessarily know where in the array you should look for this. And actually, it's a pointer. By the way, these give you iterators. So this one is going to give you that array starting from the left point. This is actually incorrect, by the way. It's got to go from the beginning each time. Because these arrays themselves don't have the left index is the index in the whole string. These arrays are just a subset of the whole sequence. So if you start off too far to the right, then you might just miss everything. So actually, it's got to start from the very beginning, and it goes all the way to the first index that's greater than this index that we gave, this left index. Now, is this left index inclusive? I think it's actually inclusive. So I think it should be greater than or equal to. So it is technically the lower bound. I actually think that I'm wrong about that. Also, the values are unique, so we're not too concerned. But the thing is, the first thing that's greater than or equal to. Yeah, no, that's actually fine. It can be that way. But this one is the first value. It's the rightmost value. It's got to be less than or equal to what we're looking for. So actually, you'd want to do lower bound. Now this is a little bit confusing because this is sorted in ascending order, right? Right now. But if we use less than, then even though it's sorted, it's not sorted in the way that the direction that we're going. I don't know how to explain that. It's kind of confusing, but basically this lower bound operation assumes that what you're looking at is sorted in the direction that you're. How to express it? So if we go to lower bound. This assumes that we're sorted in the direction that we are. All elements which the expression is true must precede all elements for which the expression is false. Yeah, must be partitioned with respect to this expression, element less than value, or compare element and value. So, and the partition is that everything is that where it's true comes before everything where it's false. So if we try to use if we try to use a greater, if we try to basically go from right to left and we use less than, it doesn't really make sense. It doesn't really work. It's a little bit confusing. It's very confusing, actually. We actually would want, because here's the thing: we can reverse the iteration on the range. In other words, you can go from right to left instead of left to right. But the problem with that, though, is it's not sorted in ascending order from right to left. It's sorting in descending order from right to left. And we can change our comparator too. I mean, our comparator we want the comparator we can do greater than. So we're searching for the not less than becomes not greater than, right? And which means it's less than or equal to, which is what we're looking for. We're looking for the first value from left to right that's less than or equal to, or excuse me, the first value really from the first value from right to left that's less than or equal to this value, this index. However, I think we do need to go from right to left because all of the things on the right side are going to be excuse me. So if we use the inverse operator, then wherever that point is that we find where it's instead of greater than or equal to, it's going to be less than or equal to. So that point where it's less than or equal to that we found it, that's true. Less than or equal to is true for a whole range of things, right? Actually, everything to the left is true. Everything to the right is false. All elements for which the expression is true must precede all elements for which the expression is false. Now the tricky thing is this is the opposite, right? So less than, they're saying this less than has to be true. Element less than the value has to be true, which is what we're looking for is the value is less than the element, less than or equal to the element, which is the negation of this. So actually this would be false all the way on the left side and true on the right side, which is really confusing, which is why you actually need to go from the right side to the left. Yeah, that's super confusing. Really make your head spin, but you can do R begin and R end. And also I think you can do C. I hadn't really considered using C as well. I think it's RC and R begin, RC R begin. CR end, yeah, and CR begin, right? I think we should be using those also, just as an aside. Constant. Oh yeah, C would come first. Yeah, or constant usually comes first, usually on the left side. Right, and you're looking for the right, and you're going to do the comparator is standard greater of int, which is I actually don't know. Yeah, I think that works. I think you can do it that way. And we're just going to put that here. What does this do? Oh, no, that won't work. Whoops. Doesn't compile. Function style cast. I think also this is, yeah, the comparator comes after. Function style cast or type construction. Oops. I don't know if this actually exists. Greater, yeah. Can we get an example where it's used? A little confused here. Hmm. Oh, actually, this is an object. Yeah, that's really interesting. Yeah, so that's really it's really confusing. This grader, okay, so this class creates a functional object, and this function actually requires an object. So it actually requires a functional object. So confusing. It's not a class. This isn't a class that we're using as a parameter, excuse me, to the algorithm. It's actually a functional object that we're handing, excuse me, to the function. That's super confusing, but I finally get it now. I think I finally understand. So we get a rightmost iterator, leftmost iterator, and then we say if then it means then we can say the well, we could do something like if they're both not like off the edge. So we can say something like this. If rightmost iterator is not equal to which array dot cend, and leftmost iterator is not equal to which array dot crend, then we can compute leftmost and rightmost. This is this distance between C begin, and then int rightmost is equal to rightmost iterator minus which array dot cr begin. There's a couple things here, like I think actually I don't know if this will work because these are constants, and also this will tell you how far you are from the right, but you actually need to subtract. So yeah, the indices. So if it's going to be s dot size minus this value. And then you can do the rest of this program here. As long as they're less than the size. You don't need to do these checks anymore. But you do need to have that these are not equal to each other. Does this work? What does this do? Okay. Can you just call this a const? Invalid operands to binary expression. Const, reverse iterator. Oh, I get it. I see the problem. This should be the leftmost, the other one should be the rightmost. These don't need to be const. Runtime error. Oh. So it's interesting that this compiles. Curious what happens here. Runtime error. Okay, that seems to be running in a loop. Stack Overflow. All right, that's always good. Oh, excuse me. I don't know what happened here. 0505005 all the way across. Okay. So 0, 1, 2, 3, 4, 5, or 0, 1, 2, 3, 4. Okay. So 0. All right. And what did we get for 0 and 5? We said B and B, I guess, is what we're looking for, or A as well, if we're looking for A. But leftmost iterator would be 0. Okay, I guess we're looking for, we found a B. Suppose we found a B. Actually, we should probably print what the character was that we were looking for here. What happened here? What happened here? A. Okay, looks like we're just looking for A over and over again. All right. Fair enough. So look for A, our leftmost iterator. So we do find A, and there's an index here. So actually the index itself, if we find something, we actually should, I actually think I'm doing this wrong. I think you're supposed to dereference the, iterator. What does this give us? Oh, it's correct. It's correct and efficient. Okay. Let's write a small subroutine. Let me see something here. Let's comment this out. Try it again. Okay. Let's do this. I'm going to check some things here. So I want to get like random characters. Oh, I don't know if I can do that in awk. But we could write a quick C++ program. Quick C++ program. Yeah, we'll do gen characters. Check this out. IOStream int main. Include random. And we're gonna say, we're not gonna make a function. We're gonna put it right in the main. It's right here. So we're gonna have a random distribution. So uniform int distribution of ints. Call that D. And we're actually going to have from 0 to 26. It's going to be our 25 actually. It's going to be our range. We're going to have a standard random device, RD. And we're going to use a generator. We're going to use standard Mesonnet twister of 19937. Or is it 19337 or 199337? I think it's 19937. Generator. And we're going to have this generator created by calling our RD once. We have our generator, and we're going to use D. Right, we'll have our generator, we have our distribution, and we're going to say for, now we can actually use args. Can use, there's two. There's int argc, and then there's a vector of, it's an array argv of, no, it's not a, it's a character pointer. I want to say it's const. Yeah. It's an array of arguments, and I think this tells us how many arguments there are. Argc is how many arguments there are. So then we'll say the second argument we want to use, we're going to say for int total nums. It's going to be argv of 1. Right, argv of 0 is actually the program name itself. Arg of 1 is the arg0 is the name of the program itself. Arg1 is the first argument we get. So we're going to say total nums is arg1, and then we're going to say for int I equals 0, I is less than total nums plus I. Going to have an out. We're going to use a string stream. Yeah, I think it's fine. So we can do a string stream. Actually, we don't even need to do that. We can just do, forget that. Just go right to the output. Well, yeah. I guess you could make it a more general with a function, but we're going to just go right to the output. And we're going to say plus A of, we're going to make a character of I, no, not I, of D of gen, it's going to be 0 through 25, plus A as a character is going to pre-print it out to the standard out. And then we're going to have a new line character printed. All right, what happens if we do this? Doesn't compile. Nice. Oh, I see. I kind of thought about that and like didn't fully process in my mind. I was like, how are we going to check that the second argument is an integer, or our first argument is an integer? And you do a string to I, and if it doesn't crash the program, then it works. Then you did it right. We can also name this actually. Oh, actually, let's try it. We'll do 100. Let's do 10. Hey, there you go. Okay. So now we can do gen characters. We're going to say gen random characters. Now we can do 1,000. There we go. Now we have easily generated our test case. Not easily, but yeah, somewhat easily. C++, taking your scripting language to a whole new level. By writing your scripts in C++ instead of oh, look, it works. Look at that. Hey, writing your scripting language in C++ instead of writing your scripting language in C++ instead of a scripting language. There you go. That's how it's done. Let's do another couple more test cases. Could actually even make our program, improve our program more by adding more arguments, so you can generate more test cases at once. So I don't have to like copy paste and click a bunch. All right, let's go for it. Let's see if this is correct. It seems to be okay. I think I made a mistake. Oh, no, we're fine. Okay, nice. I was gonna say I think I maybe made a mistake because of like there could be cases where no, I guess we're fine actually. No, never mind. No, never mind. We're fine. Alrighty. What's weird about this is I was expecting this to be faster, actually. Thought this was a pretty significant improvement that we performed here. I somewhat can't believe that this is so slow. Let me see if I can improve this slightly, by the way. How about this? Let's try this. Whoa. That is not faster. Or, well, yeah, I guess it's fine. I don't know if there's actually much of an improvement, by the way, on what we were just doing. No, not really. This is something of an improvement on we had before. I'm fairly certain that this is n log n, by the way, this solution. Yeah. N log n times the size of the character set. That's what I think. Could be wrong. I think so. All right, what does the discussion say? I was gonna go lay down, I think, after writing this, but brute force to DP, super simple solution using reverse string. DP linear quadratic time, space with one array, quadratic to linear space. It's pretty good. 100% with preprocessing, top down and bottom up. Quadratic. What I have is, I'm pretty sure, not quadratic, by the way. fairly certain it's not quadratic because each iteration you're guaranteed to remove 2 characters at, in the worst case, at least 2 characters, and it costs only a logarithmic amount of time to perform that. There is an issue of, like, we did have to memoize such that we didn't have like redundant work that we were doing. Like I said, it makes the character set, instead of the character set being exponentiated, it's just a not an exponentiated constant, but just a constant. But I don't think it's actually quadratic time. I think it's not quadratic. I think it's n log n time. Could be wrong though. I don't know why everyone else is so much faster than mine though. I think theirs is faster because they're using dynamic programming rather than the memo. I think it's the memoization that we're doing. Also, I'm using recursion, and I guess you don't necessarily need to use recursion. O of n and SC of n, O of n, O of n, bottom up search, recursive driver. Oh, dude, that's like a super straightforward. Doesn't give oh, I'm sorry. Okay, no, never mind. This is fine. This really should be. This is a little bit confusing. This should be one function, I think, because this calls this one memoization. Actually, I think I'm wrong about this being not quadratic. I don't think it's quadratic, but it's, I don't know. I'm just wrong. Maybe it is quadratic because I think the memoization kind of forces you to be quadratic. It's not quadratic. No, it's not. Why? I don't know. It's because you're multiplying by the character set. But I think the issue is that because you have this left and right, these left and right values, do you not go over all of them? I guess that's the question. All the possible subsequences, right? All the possible selections of left and right. How do we know we don't go over all of them? The reason we know we don't go over all of them is because we only have 26 characters to work with at each step. And so even though and each step you remove at least 2 characters. Maybe I'm wrong. Maybe this is just quadratic. I don't know. Yeah, I think it is just quadratic because you can't guarantee that you aren't just going to reach every. You aren't just going to go through every sort of possible left and right subsequence or sub every possible selection for left and right. No, it's not true. It's not true. You only go through a linear amount, a linear factor times 26. I can't tell. I can't figure it out. We can't use a DP. Like if we DP over the string size by the string size, then obviously we're going to end up with quadratic space and running time. But I think because we know that at every step we have at least 2 characters are gone, right? So we know we have a depth of a linear depth. The question is the breadth. Do we have a breadth in our tree that's linear, that I don't think so. It's not even about having that. Well, maybe actually, I don't know. I don't think that it's possible for it to be quadratic the way that we're doing it, because even though at each step you remove at least 2 characters, there's only 26 possible selections that you could have for the next step, and all of those are smaller, right? It's not a linear number of things to select. So I think the answer is actually no. I think the answer is not, that this is not actually linear quadratic space that we're using. If we do it this way. It's a little bit slower, I think, only because we're not using more characters in our test cases. I think if you use more characters in the test cases, this would actually be a faster approach. But yeah, I actually think this is a faster approach than what the other solutions have. So it's kind of ironic that this is, I think is n log n. I think it's asymptotically faster, but we're on such a small test case that actually the DP algorithm, where that actually is quadratic, would actually be a little bit faster. Just because there's a lot, I guess this has to do. I think this is faster though. I think we did it. I think we actually found the optimal solution. It's actually better than. It's kind of hard to prove it, but I'm pretty sure that this is n log n time, and this is also it's n log n time, and it's also linear space overall, even though it looks like it's quadratic space. Yeah, pretty interesting. Really interesting question. Hard to kind of explain though, or prove maybe. But it's actually slower than the other solutions, which is weird. But on smaller test cases, for whatever reason, it's slower. I think it has to do with just overhead, some kind of overhead. It might be this memoization too. I mean, that could be it too. If I use an unordered map instead of a map. But I think asymptotically this is faster. Yeah, it's a lot less memory. Excuse me. Anyway, all right. So pretty interesting solution, pretty interesting problem. I think that'll be it for me regarding the palindrome subsequences. Yeah, that'll probably be enough. That's probably enough. I think I did better than the discussions, believe it or not. Again, on these test cases, it's not faster, but I do think it is asymptotically faster. Can't really prove it. I'm like struggling to prove it, but like something tells me there's a way to show it that it has actually n log n time overall, and also doesn't use quadratic space. Uses there's an extra like logarithmic term that's in here because of how we memoize, but like barring that extra logarithmic term, right? Obviously, we can use an unordered hash map and hash this tuple. Barring that, yeah, then I think we're okay. I think we're in good shape. Excuse me. I think we actually do have a quadratic, excuse me, n log n times the character set size, runtime, and then also O of n space algorithm. Pretty interesting. Pretty interesting. I think that's, but it's not O of n. It's O of n times the character set, by the way, which I think is in both cases, right? That's here, and also here. That's also the case. But I want to say the proof that it's it's O of n log n times the character set size is that that because of memoization we can say that we're always at least removing 2 characters. So each step, even if we're doing it 26 times, is like 26 times some 26 times, like, you know, opening closing parentheses, some amount of work that needs to be done that's proportional to the problem size plus f of, I guess, this f of sort of n minus 2, right? At least 2 characters in the worst case. And that work that has to be done it seems to be logarithmic work, right? We can do this pre-computation step and guarantee that a logarithmic bound, so log of n time, O of log n time, plus something that's basically n minus 2, which gives you, and 26 times that, which gives you a recurring sequence of 26 times log n plus 26 times log n O of log n plus f of n minus 2, or we could do n minus 1 even, really. So that recursion basically gives you a sequence that's 26 times log of n plus 26 times log of n plus 26 times over and over until you get all the way down to a O of log n factored out times O of n, really, right? That's how many times you're adding log n. You actually get something kind of funky. You get that O of log n, but you actually get the summation of the 26 plus 26 squared plus 26 cubed all the way down. You get that, what do you call that? You get that times log of n. That's actually a, what do you call it? That's actually a geometric sequence of, that would be the character set raised to n. That's actually what I actually thought it was the other way around. I thought it was 26 raised to the character set. Excuse me, yeah, I just thought it was the size of the character set raised to, or 2, is it 2 raised to the character set size? I don't know, some exponentiation of the character set. Yeah, I was thinking it was 2 raised to that character set, not actually the character set itself raised to n. So actually, maybe this is quadratic. You can't do better than quadratic. I'm trying to do the math, but it doesn't really work. Yeah, maybe not. Maybe it doesn't matter. You do it's 26 times, it looks like O of log n plus f of n minus 1, and this is f of n. So that gives you 26 times O of log n plus 26 times O of log n. Maybe I'm just wrong, I don't know. F of n minus 2, just 26 O of log n dot plus 26 O of log n, and this is just f of 1 or f of 2 of something, which is probably just basically 0, right? F being the amount of work that needs to be done, roughly speaking, which then gives you 26 times O of log n here plus 26 squared over log n plus dot 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 all the way down to 26 raised to, now I think this is n really raised to the n of log n, which actually gives you O of log n times the character set raised to the, it looks like n plus 1. It's roughly n plus 1. Yeah, so I actually don't think it matters then. Only this term becomes O of n squared. And so really actually just end up with O of n squared log n, I guess, or what have you. May have actually been O of n cubed before that we had. This is the memoization here is necessary to keep this sort of sane and bounded. This s raised to n plus 1 is always going to beat O of n squared. So this is just always this is just O of n squared then, I think. Yeah. The fact that you're going through so many characters each time. You know, it's funny, I didn't really think about that this is actually, this really is 26 function calls. This isn't one function call. That's kind of what I think I was getting confused about. This is actually 26 different executions of this call, so this is quite the recursive function. So yeah, I don't think you can do better than quadratic on this. So never mind. That's why this is so slow. In which case, then you would have to defer to those DP solutions. Those would be the fastest. There's one that was O of n squared, O of n. I don't think you can do better. At least you can't do better with this approach than O of n squared, O of n. I'm kind of upset. Not upset, but kind of like disappointed. Yeah, a little bit confusing, I realize, but the issue really is that you're calling this function 26 times. That's a lot. Yeah. The only way to really reduce that. Amount of processing is to basically use memoization to make most of those calls effectively constant time. And that brings it down to O of n squared. Interesting. Now, it's kind of hard to explain it, but basically there's no way to do better than O of n squared if you're making a lot of function calls, but you're making them constant because you're using memoization, and so these like recursive calls don't actually take that much time because they're memoized. Like if you could make this linear time to make this call, then you would have n log n. Like that's kind of what I was going for. I was like, I think if this is linear, then it's just n log n, but it's not, I guess. Or I don't just guess. I don't think so. I don't know, man. That's super hard. It's super hard. I don't know. I can't do the math. I don't know it. Maybe it might not be impossible, but it's hard. It's definitely really hard to get exactly the correct idea here. The reason I'm thinking that is it's memoized. So calling a lot of these functions will actually take constant time. Excuse me. But I think the issue is that you basically end up filling the search space before you're. I want to say something like once the search space is filled, then all of these function calls become constant, and so you take at least O of n squared time to do that to make them all constant, and then after that they're all just constant calls. Excuse me. I think that's true. I think that's true. And even if each of those filling that space, even if each of those calls were optimal, where they were all constant, which they kind of are, they more or less are. Even in that case, then you still have a situation where excuse me, you still have to call all of those things at least once, and that's O of n squared. So I think this is O of n squared. Obviously, again, the way I've done it, there's like an extra logarithmic term, and there's some degree of like logarithm shenanigans going on here in this pre-computation, but I think ultimately it's just O of n squared. Well, okay. Anyway, I thought maybe there was a way to beat it to do better. Let me end it here and go take a nap. I don't know. I kind of just I don't know. Thought or wished or assumed that there would be a faster way, better way to do this, but I think this is just it. There's no other way around this. So yeah, let me go. Thank you for watching. Talk to you soon. I'm probably just gonna go take a nap, relax for a bit, and then come back and look at there's some other questions I wanted to look at. So yeah, so thank you for watching. Take care and talk to you soon.